Okay. Yeah, so I'm continuing the topic left from last time, and the topic we discussed is a continue of project management using CPM and PERT methods to graph AON network. And for the next step, so I skipped the AOA because we don't use that for this class. Okay. So the next topic will be performing a critical path analysis to determine the project schedule and calculate the time of completion for different tasks. So let me check one of my students. Please mute yourself if you don't have a question. If you have a question, feel free to ask. So some students are still confused. They don't know where to find the link. I emailed the link to everyone, so inform them. All right, so to perform a critical path analysis, the critical path is the longest path to the network. The critical path is the shortest time in which the project can be completed. Any delay in critical path activities delay the project, and critical path activities have no slack time. And what we mean by slack time is flexibility. So those critical activities, we call them critical activities. Critical activities are activities that don't have any flexibility. If we have delayed on those, if we don't have the right timing in completing the project on those tasks on time, the whole project will delay. So they don't have flexibility. So they don't have slack time, right? We call them critical activities. And these critical activities, the route through them, the path through them is called critical path. So we try to find out what our critical path is. We're going to calculate it and find that critical path. And we also need to remember that this critical path, after we found it, which includes the path of all critical activities, is the longest path to the network, which means that's the maximum time of completion of this project. The critical path is also the shortest time in which the project can be completed. Any delay in critical path activities delays the project. Critical path activities have no slack time. Now, up to this point, what you learned was you learned how to graph the network. Now, the time of each task is also given to you. Earlier, the tables earlier told you which activity is before or after which activity. Now, you're seeing here that the time of each activity is given to you. So using these times given, we can start calculating the time of completion of this project. So before that, we need to start with some definitions. ES stands for earliest start. It's the earliest time at which an activity can start, assuming all predecessors have been completed. Earliest finish is the earliest time at which an activity can be finished. Latest start is the latest time at which an activity can start, so as to not delay the completion time of the entire project. And latest finish is latest time by which an activity has to be finished, so as to not delay the completion time of the entire project. Okay, so you can see it here. This circle represents one of those nodes that we put activity name on it. So you can see we divided it into 5 parts, and in fact it's 6 parts. So on the top we put the activity name or the symbol of activity. Below that center we have the activity duration, time of completion of that task. On the left hand side we have information of starting the activity. On the right hand side we have information of finishing the activity. So start, the earliest you can start, after how many days, how many weeks, how much time you need to start the activity. Sometimes starting an activity can have delay, so that lower part down here, LS, latest start, is if when you want to start but there is a delay, right? And on the right hand side you have the finish. So if you finish it on time or early, after how many weeks, how many days, how many months. And here you have if there is a delay in finishing the task, how many days, how many weeks. Feel free to ask questions if you had. So you're gonna have, let me open the chat box here. Okay, so we have 2 processes here. One is called forward pass. So the forward pass, we fill up the upper part of these 2. So A is already a name, so it doesn't change. The number down here, activity duration, is given to us in that table, so it won't change. What's going to change is earliest start, earliest finish. So moving forward from the beginning of the network to the end of the network, we start calculating earliest starts and add duration of activity and calculate earliest finish. When we are done with the whole network on the top, then we have a backward process. A backward process is calculating the bottom part. All right. So the first part is the forward pass. So forward pass, begin at starting event and work forward. Earliest start time rule. So there is a rule to fill up these numbers. Okay, these parts. So if an activity has only a single immediate predecessor, its earliest start equals to earliest finish of the predecessor, right? If an activity has multiple immediate predecessors, its earliest start is the maximum of all earliest finish values of its predecessors. So ES, earliest start, is the maximum of EF of all immediate predecessors. So let's see what that means. One more rule is earliest finish, EF, time rule. The earliest finish time, EF, of an activity is the sum of its earliest finish plus the time of the activity, and that makes sense. So at the starting point, we have everything zeros because at the beginning, there's no specific activity. Then we start with activity A. So what I did, I copied the table of activities to the right-hand side of each slide. So you can see A, building internal components. It takes 2 weeks. So where did this 2 come from? From the table. The table is showing that there are 2 weeks. It takes 2 weeks for us to complete task A. So starting point, we can start it at the beginning because it's the first task to be completed. So it takes 2 weeks. After 2 weeks, what's the earliest you can finish it? 2. 0 plus 2 is 2. Right? Then the next one is activity B. How do we know these? These are information that you learned earlier in the last session from a table that tells you how to graph the network. So you already know how the network looks like. You're just filling up numbers. So the next step is B. B is also a starting point, if you remember that. If you don't remember, you can go back to the previous slides and see we designed the network this way. So A and B are starting points. So the 0 is because of that. The time it takes for B to be completed is 3. It's right up here. We put 3 down here. 0 plus 3, 3. So that's how we calculate A and B. Very simple. How about C? C only has one earlier task, and that's A. So as soon as you finish A, you can start C. How long does it take to finish A? 2 weeks. So that 2 goes here for the earliest. The earliest finish of A becomes the earliest start of C, because C is only dependent on A. If there is another node that is C dependent on, then we take the maximum. So in this case, it's just A. 2 goes here. How long does C take to complete? 2 weeks, right here. 2 weeks. So 2 plus 2, 4. So we can start C in week 2. If A is completed, it takes 2 weeks to complete C. 2 plus 2 is 4. And we can continue this process. But let's see a case that has 2 earlier tasks, and that's D. So task D, if you look at the network we created earlier, is dependent on both A and B. So D is dependent on A and B both. So D cannot start unless A and B both have finished. A takes 2 weeks, but after 2 weeks, B is not completed. So D has to wait for B to complete as well. So which one goes for the earliest start of D? The one that is higher or takes more time. Which one takes more time, A or B? B. B has 3 weeks, so 3 goes here. Why? Because it takes more time, right? So D has to wait 3 weeks until A and B both complete, and then we can start D. So 3, and then D takes 4 weeks, so 3 plus 4 is 7. 7 weeks to complete D. Don't feel free to ask questions if you have anywhere. Okay, so that's how A, B, C, and D look like. The rest of the process is exactly the same. You just find the earlier task, find out what's the earliest finish, add it to the duration of each task, and calculate them. So if you complete that, you would get this information, this network with these numbers. So you can see all of them are being calculated. I'll give you a minute to check numbers, make sure you understand them. All right. I think you can see that all numbers, they make sense. Ask if you have a question. So that was the forward pass, okay? That was a forward pass. Now, going backward from the end to the beginning, we start calculating the lower or the latest start, latest end. Latest start, latest finished. So LS, LF. So there is a rule for backward pass as well. So we begin with the last event and work backwards. Latest finish time rule is if an activity is an immediate predecessor for just a single activity, its latest finish equals its latest finish equals the latest start of the activity that immediately follows it. If an activity is an immediate predecessor to more than one activity, its latest finish is the minimum of all latest start values of all activity that immediately follows. So latest finish equals to the minimum. So the previously for forward was maximum. For backward, it's the minimum. The minimum late start of all immediate following activities. Latest start time rule is the latest start time, or LS, of an activity is the difference of its latest finish and its activity time. So remember previously when we were moving forward, it was plus, right? The earliest start plus activity time gave you the finish. Now we are going backward. So we start with the finish. Finish minus activity time is the start. That's how the calculation works. It's very simple and it's simple to understand. So that's the starting point. So we know that the latest finish equals to earliest finish of the last node. So 15 goes down here. Now, what's the earliest? The earliest start of H was 13. What's the latest start of H? 15 minus 2. 15 minus 2 is 13. So that's where 13 came from. 15 minus 2 is 13. The next one. So the only earlier node after F is H. It's only one. So we just look at the earliest start, latest start of H, which is 13. So 13 goes as the latest finish of F, because that's the maximum time it takes to start H, right? So that amount of time you have for F, because H is only dependent on F. So F have more flexibility. It can last up to 13 weeks to finish. And how do we know that? Because H can wait 13 weeks to start. So there is 13 weeks time at this point, okay? All right, so we already know that F earliest finish is 7, late finish is 13. 13 minus 3 is 10. 13 minus 3 is 10, right? So let's continue. We can do it for G as well. For G, again, there's just one, right? 13 goes here. 13 minus 5 is 8. Let's go back, go forward and see what we have down here. So 13 is down here. Why? Because there's 13 weeks maximum here, and 13 minus 5 is 8. Now for the next part, let's have an example with two of them. So which one we can calculate. For example, E. The next of E is 8. So 8 goes here, right? There's just one connection between E and G. So 8 goes here. 8 minus 4, 4. But for C, C has 2 connections, right? C has 2 connections. One of them need to start after 4 weeks. The other one can start after 10 weeks. So which one C should support? The one that is earlier, right? Minimum of 4 and 10, which is 4. That's what we put 4. So minimum of earliest starts, whichever is there. Earliest start, the one that is lower, is 4. So 4 goes there. 4 minus 2, 2. So we fill up C as well. Does that make sense, everyone, up to this point? The rest is just the same. Okay, you can answer on the chat and tell me that makes sense. Just want to make sure that you're all doing good. Perfect. Thank you, Kevin, Anita, Vlada. Thank you. Perfect. So it wasn't difficult, right? It's so simple. So if any of you forgot this or feel confused tomorrow, I uploaded the video of the same example by another instructor. It's a perfect video. Exactly the same thing is explained in a different way. So I will record today's class and I will upload this video as well. So you have 2 videos on this topic and you have no excuse for not understanding these topics. And look, this is very important to understand that all this simple process from the beginning when we started this chapter, all the process is simple, but remembering that from the beginning where to start, what to do, it becomes a little confusing because there are too many things to do, right? As a result, practicing and writing everything on one page of paper can help you to remember all this process, especially for exams. If you have like 2 hours time, for 2 hours time, that one of your questions is this, you need to have enough practice to complete this in maybe 10, 15 minutes. So you won't have like 2 hours to do this. You have like 10 to 15 minutes to do a question like this, to complete a question like this. In addition to that, remember, you can add project management, which is chapter 3, to your CV as a separate ability that you have. Separate, I can say, one of your, in fact, extra ability to do something, right? So, and next to your project management, one of the things you can write is critical path analysis. You can just write critical path analysis. I know how to perform critical path analysis. Of course, there's not one unique way of doing critical path analysis, but if they ask you, you can say, I use PERT method or CPM method. And as long as you say that, if they ask you how to do it, if you learned it during the interview, you can show them how you can do it. Then whatever software they have, you can always learn that. They give you time to learn that. No worries about that. As long as you know the topic, you have it on your CV, you have an advantage, okay? And that advantage, many students, they don't know. Many people, they don't know they can put these on their CVs and their CVs can stand out and they can become a project manager. So learning these is not just for getting a good grade, it can help you to get a better job with a higher salary, okay? So learning these is not just for a grade, it's not just for this class. Don't think about just this class. Learn this for getting a better job, making more money, and make your time more valuable, okay? So computing slack times. Again, slack time is, if you want to say it very shortly, slack time means flexibility. Which task is flexible and which task is not. So If we can calculate slack times and slack time is 0, that means there is no flexibility. If slack time is any value, any number, that means that task is flexible. Why do we need to know slack times and knowing which task is critical task? It's important to know because as a manager, you need to make sure for critical tasks, make sure you have a professional person doing it, making sure the machines, all the facilities, everything is working well, everything is correct, and you have more control over it, you have more data collection on those tasks, and make sure everything goes well there. You don't want any delays in your critical activities and your critical path. So, because if your critical path fall in trouble and delays, your whole project will have delay, and you don't want that. So for that reason, we're going to calculate slack. What is slack in definition? Slack is the length of time an activity can be delayed without delaying the entire project. Or in other words, it's flexibility. If you want to say it in one word, that's the flexibility of each task to be completed. So we already calculated earliest start, earliest finish, latest start, latest finished, and using those numbers, we can simply calculate the slack times. We can see those slack times that are zeros. That means that task, for example here, A has no flexibility, so it's a critical task, and that task is on critical path. Is it on critical path? Yes. Why? Because the slack time is 0. So on exams, on homework, you will have questions like this. Either the table, this table is given to you, ask you to calculate the slack times, and then ask you to put yes or no. So for zeros, you put yes. For ones, you put those non-zeros, you put no. And then from here, we can actually create and represent the critical path on our network. So this is our network. All the calculations are there. So those, look, 2 minus 2, 0, right? 4 minus 4, 0, right? 8 minus 8, 0. 13 minus 13, 0. 15 minus 15, 0. These are the ones, A, C, E, G, H. These are the ones on the critical path. These are our critical activities. If one of these delays, we would never meet the 15 weeks time to complete the project. That would delay the project, and we'll go further more on activities to be complete. Any questions? Any concern? Any question? Any comments? Does that make sense? Is that good? Thank you, Eric. Kevin, thank you. Jorel, all good. Perfect. All right. So using these numbers, using all these numbers, you can create a Gantt chart. That's your Gantt chart. So Gantt chart is nothing but a list of all of your activities and showing your calendar, showing the time. This is time, week 1, week 2, week 3, up to week 15, 16. And then showing where this task starts, when it's gonna end. And that's using what? Using your early start, early finish. Now you want to know if there is a delay in some tasks, what's going to happen. So you can create another Gantt chart. So the other Gantt chart would be the Gantt chart for delays. That's the latest start and latest finish. Latest starts and late finish. So you can see for activity A, there's no late start, right? Because activity A is a critical activity. Next is variability in activity times. So not all methods consider variability in activity times. CPM, as we said earlier, is a critical path method. Assumes we know a fixed time estimate for each activity and there is no variability in activity times. Of course, that's less realistic. And using those calculations, when you are completing your project, your team and yourself are under higher pressure to make sure that everything is done perfectly. PERT, however, uses a probability distribution for activity times, and it allows the project to have variability. That means delays are possible. Our estimation of time of completing the project is an estimation. It involves error. It has an average. It has upper bound, lower bound, and if the numbers are normally distributed, then we can say, and then we can find the standard deviation and say with 95% probability or with 70% or 68% probability, this is how long it takes for this project to finish. So sometimes your manager will ask you with 99% probability, when can you finish this project? Then you can actually numerically calculate it and tell them, and that would be pretty much accurate. Of course, these methods are simplest methods for project management. There are more complex for problems with higher complexity that they can do the same thing but with higher accuracy, but there are higher level of math and statistics required for those. So these are actually simple enough for us to learn for this class. All right, so now let's assume that we accept variability in activity times. That means the time of activity that we calculate is not unique. It's actually, there's an upper bound, lower bound, and a center point. The center point can be mean, can be median, can be other statistical measures. So let's say the lower bound, the earliest you can finish a task is called optimistic time. So optimistic time A, we show it with A, that's your lower bound. If everything goes according to plan, and pessimistic time is your upper bound. It's assuming very unfavorable conditions happen, delays happen. If those delays happen, then how long it takes for us to complete this task? As much as B. A is earliest, B is latest. And most likely is normally like average, right? So most likely, or from historical data, we have seen that most of similar tasks have been completed in that amount of time. That's most likely. So most realistic estimate of completing a task. So A is lower than M is lower than B. Okay. Now let's say that these numbers are given to us. Of course, on exams and homeworks, A, M, and B are given. Okay, these values are given. These values are given, and all you have to do is to calculate the expected value and variance, and later standard deviation. So expected value of activity time has a formula. Let's say A, M, and B are given to you. So you just add these numbers. A plus 4 times of M plus B divided by 6. That gives you expected value of completing activity time. You want to calculate variance, there's a formula for it, right? So V equals to B minus A, highest minus lowest, divided by 6 squared. That's your variance. It's nothing difficult, it's just a formula. You just need to know, recognize from the question, which one is A, which one is M, which one is B, substitute the numbers, calculate T and V. And that's how it looks like. Let's say this is, of course, this is not normally distributed, this is skewed, but let's say if this is like a normal distribution. That's your lower bound, that's A, optimistic. And that's your upper bound, pessimistic. And that's your most likely. Could be your average or median. That's your most likely, the middle. Okay, so the area under this curve is 1, that's 100%. So the closer you are to most likely, of course, there is a lower chance to. The more we go to the left, that means you complete this project earlier and chances are lower. Probability is lower. All right, computing variance. So each task, each activity has its own A, M, and B. Optimistic, most likely, pessimistic, right? As a result, for each one, you can calculate expected time. And for each one, you can calculate the variance. So you have variance of all of these different activities. All you need to do is to add them up. Add these variances. That's the variance of your whole project. Add all of these variances. That become the variance of your whole project. So in the next step, let's see what we have here. Yeah, so the project variance is computed by summing the variances of critical activities, right? Not all activities critical. So which one were critical? How do we know which one are the criticals? Those are the ones. Let's go back and see which one is critical. Go back. So we earlier find out, let me write it down. So A and C and E and G and H. 1, 2, 3, 4, 5. So these 5 are on critical path. We just add those variances because that's your longest path. So that would create a higher variance. All right. So that's correct. So the variance of A is 0.11. The variance of C is 0.11. The variance of E is 1. G 1.78. H 1.11. The sum of these critical activities variances are 3.11. So 3.11, what is it? It's variance. What is variance? Variance is a square of standard deviation. So if you have variance, you can calculate standard deviation. How? With getting a square root. So a square root of variance of the project is a standard deviation of the project. One more time, a square root of project variance is a standard deviation of the project. So what's the standard deviation of this project? 1.76. So assuming normality for activity times or variances of activity times, we can simply come up with that base rule that 2 times the standard deviation includes 95% of activities, right? 99.7% is in the range of 3 times mean or expected value plus minus 3 times standard deviation. So let's see what kind of question we're going to face. So here is saying that PERT makes 2 more assumptions. So we can use that method if we have normal distribution. So total project completion times follow a normal approach distribution. We're using this because we want to use the z distribution to calculate the z value and calculate the probabilities. Activity times are statistically independent. So in reality, sometimes they're not independent. Here we assume that they are independent. If they're not independent, the calculations would be different. Formulas we use would be different. So that's why we need to consider this assumption. All right, so that's our normal approach distribution. That's our expected completion time, 15 weeks, right? If the question says like 16 weeks, what's the probability of finishing this task in 16 weeks, right? 16 weeks is somewhere around here. So the probability to finish the project in 15 weeks, of course, that's the center, that's half, that's 50%. If it says 16 weeks, that's a little to the right, that would be probably somewhere around 65 to 70 something, somewhere between 65 to 75% probability. All right, depends on the standard deviation that we have. So you can see here the question is asking, what's the probability this project can be completed on or before 16-week deadline? So what's the formula? The formula is due date, that's given to us on exam, on questions. Expected date of completion is calculated by us, given the values of variances, divide by standard deviation. So that's 16 weeks minus 15 weeks, divided by 1.76. Right, that's 0.57. What is 0.57? That's how many standard deviation we are far from expected value. How many standard deviation we are far from the expected value. And that can tell us what's the probability, because we can find that 0.57 from the z table and find the probability associated. All right, so on the next slide, you can see that we have, here we have 57, so that's on, this is z table, this is z values, 0.5, and 0.7 is up there. The intersection is 0.71, right? Approximately 71.6% probability to finish this project in 16 weeks. All right, make sense, everyone? Make sure you understand these. Does that make sense? Yeah, okay, good. Good, good, good. Hello, Eric, Joel, Jet, Anita, thank you. All right, so I hope it makes sense for everyone. So if that makes sense for you, let me change the question. So if I change the question to 18 weeks, so the question is, calculate the probability this project, I'm writing it for you and I've sent it to you, okay? Probability this project to be completed before 18 weeks. Probability this project to be completed. I send it to your chat, to your group chat. Probability this project to be completed before 18 weeks. Can you calculate it for me and tell me what's the probability of it? 18 weeks. I give you 5 minutes. So what is 1.7? 1.7 is your z value, right? Now, what's the next step? Yes, Kevin. The next step is to calculate the norm that s the dist, I think, of this z value. And then we need to put true because it's a continuous. Normal distribution is continuous, so, and we want area. So you need to put true. That's correct, Kevin, Sandeep, that's correct. 95.54, approximately, right? Depends on how many decimals you rounded to. So normal that s dot dist of z value and true will give you 0.95. 95% is the probability of finishing in 18 weeks. Good job. These are good stuff, right? Good information to use for management. They're good for management. Any questions? Anyone has any questions? Any questions? All right, good. Perfect. So let me ask you another question. So that's what we just did. So that's what it means. So for us, it was 18, and that blue part, the area is 95%. For 16 weeks, it was 71.57%. If you were given a limit like 14 weeks, means earlier than expected value, right? Then earlier, of course, you had a lower z value would be like negative, and if it's negative, then that goes to lower, less than 50%, right? And if it's not less than 50%, that means you make some mistakes somewhere. So let's answer a question like this. This question I'm asking, with 99% probability, this project can be completed on or before how many weeks deadline? So if probability is given and the number of weeks is asked, how would you calculate that? So that's the next question. So in here, I'm saying 19.077. Let's first try that on 19.077. Try that. I'll give you a few minutes to calculate the 19. So 99% probability is given. Probability is given. What is asked? What's asked from you is number of weeks or how many weeks? How many weeks? With 99% probability. Of course, I calculated 19.077. Let's see if I did it correctly, okay? Let me see how many of you can calculate that number. Give you a few minutes, then I'll show you the work. And then I'll change the question from 99 to something else, and then you calculate it together. All right, so as you can see, you can do the inverse process and probability is given to you. So you use norm.standard.inverse of 0.99, and that should give you the z-value. So the z-value is, the z-value here is 2.32. How many of you have this z-value? Did I do it correctly? All right. Okay, now you have z. How did you calculate the 19 days? Anyone can tell me how you calculate the 19 days? Do you know which formula to use? Go back up. Go back up. That's your formula. So in formula, let's see what you have and what you don't have. So what I'm going to do, I'm going to type in your chat the formula we're going to use. So look, I want to find the due date, right? I want to find the due date. Now I have z, I have expected, which is 15. I have sigma, which is 1.76. So I solve this equation for due date. That's it. So you multiply both sides by 1.76 and plus 15. So that would be, so your due date equals, I'm typing it for you and I send it to you right now, okay? Z value times sigma, which is standard deviation, plus expected. Did you get it? Did you get the formula? Due date equal to z times sigma plus expected. That's your formula. So anytime this type of questions gave you the due date, ask you for probability, you use this formula in the slide. If the probability is given and due date is asked, you use the formula I just sent you to the chat group. Okay. Any questions? Any concern? Any comments? So did you get the 19? Use that formula. So you know how I got this formula, right? The formula came from multiplying both sides by sigma and adding expected to both sides. Did you find the 19? Tyler found it. Who else? Anita. Okay, good. Carlo. Perfect. 3. How about the rest? Kevin got the 99. So my next assignment, I'll change the 99% to a different number. And I want you to do it yourself, okay? So this time, let's say the same question, but probability instead of 99. Let's use 85%. So if probability is 0.85, then how many weeks is the due date? All right, I give you a few minutes, maybe 4 or 5 minutes, so you know the process, and it's pretty much simple to do. Get this done, and let me know